Good morning. It's June 12th, and this is your daily brief in science. Here's everything you need to know. NASA has made a significant release of over 1.5 terabytes of data from the James Webb Space Telescope as part of the Cosmic Evolution Survey, or COSMOS. This dataset offers an unprecedented view of the universe, including a galaxy catalog and an interactive viewer for users to search specific images and view their properties. The data covers 0.54 square degrees of sky with the near-infrared camera and 0.2 square degrees with the mid-infrared instrument. Cosmos Webb is one of around 100 projects leveraging the $10 billion JWST to observe high redshift galaxies across a vast cosmic area. This approach contrasts with other surveys that typically focus on smaller regions for deeper observations. A primary objective of the COSMOS project is to understand the structure of galaxies in relation to the reionization process, which occurred approximately 200 million years after the Big Bang. The COSMOS Webb program is a collaborative effort supported by NASA, involving the University of California, Santa Barbara, and the Rochester Institute of Technology. While raw data from the JWST was previously public, the COSMOS Webb project enhances usability by calibrating and correcting imaging artifacts, resulting in cleaner data for scientific analysis. These artifacts can include non-astrophysical elements, such as ghost images from bright stars, which could affect observations. This dataset provides the largest deep view of the universe available to date, showcasing nearly 800,000 galaxies with complete NIRCam and MIRI mosaics. The JWST NIRCam mosaics are organized into 20 zones, with images accessible in 4 filters: F115W, F150W, F277W, and F444W. To aid users, COSMOS Webb includes a full photometric catalog detailing various measurements and parameters for the observed galaxies, aiming to study those formed shortly after the Big Bang during a pivotal transition in the universe's evolution. The project has utilized the Candide supercomputer in France to compile images into a comprehensive mosaic, contributing to this extensive dataset now available for scientific exploration. A recent study published in PLOS Biology has revealed critical vulnerabilities in the deadly fungal pathogen Cryptococcus neoformans, which is linked to nearly 4 million deaths each year, particularly affecting immunocompromised individuals. Conducted by the Stowers Institute for Medical Research and the University of Georgia, this research identified over 1,400 essential genes in C. neoformans, with more than 300 of these showing no similarity to human genes. This discovery points to potential targets for new antifungal therapies. Among the significant findings, researchers pinpointed 302 ideal therapeutic targets, with approximately 30 genes conserved across various pathogenic fungi. This suggests a promising avenue for broad-spectrum antifungal treatments. The study utilized a cutting-edge technique known as transposon mutagenesis sequencing, or TN-seq, which allows for the rapid identification of essential genes across the genome, streamlining the drug discovery process compared to traditional methods that analyze individual genes. By damaging the fungal genome with transposons, the researchers effectively mapped which genes are vital for the fungus's survival, likening the process to assessing bullet damage on fighter planes during World War II. This research, supported by multiple NIH grants and the collaborative efforts of both the University of Georgia and the Stowers Institute, highlights the ongoing challenges in antifungal drug development. The genetic similarities between humans and fungi complicate the identification of fungal-specific essential genes necessary for effective treatments. Lead author Dr. Blake Billmeyer emphasized the urgent need for novel antifungal therapies, as current options frequently fall short, contributing to around 150,000 deaths annually, particularly among HIV patients. Dr. Billmeyer's future research will also investigate how fungi adapt to rising temperatures, a key factor in understanding their pathogenicity as global temperatures increase. Overall, the study's findings could significantly accelerate the drug discovery process for antifungal agents, paving the way for more effective treatments. A recent study from Cincinnati Children's Hospital has unveiled significant findings regarding the impact of antibiotics on gut bacteria and the immune system. Researchers, MD-PhD students Jake Stevens and Erica Culberson, discovered that antibiotics disrupt gut microbiome function, which is crucial for teaching the immune system how to combat respiratory infections effectively. The study identified Bifidobacterium, a beneficial gut bacterium, as essential for producing inosine, a molecule vital for the development of immune cells. When infants are exposed to antibiotics, the absence of inosine leads to impaired immune function, making it difficult for them to develop necessary immune cells. This impairment extends to the development of tissue-resident memory cells, which are essential for rapid immune responses to reinfections, with deficits potentially persisting into adulthood. Using data from both mouse and human infants, the research revealed that those exposed to common antibiotics like ampicillin and gentamicin had significantly lower levels of protective CD8 plus T cells in their lungs. The immune deficits observed in antibiotic-exposed human infants mirrored those found in mice, underscoring the universality of these findings. The implications of this research suggest that immune deficits caused by antibiotic exposure can lead to permanent changes in the immune system. Interestingly, inosine supplementation has shown promise in restoring normal T-cell development and enhancing infection resistance in antibiotic-exposed mice. Senior author Hitesh Deshmukh highlighted the importance of targeted supplementation to protect vulnerable infants, though further testing in human clinical trials is necessary before making any recommendations. Researchers are advocating for careful antibiotic use during pregnancy and infancy, proposing probiotics or prebiotics as alternatives to support healthy microbiome development. Further research is essential to evaluate the benefits of inosine supplementation in human infants and to develop strategies aimed at protecting them from respiratory infections. A recent breakthrough in brain-computer interface technology has transformed the life of a 45-year-old man suffering from severe speech disabilities due to amyotrophic lateral sclerosis, or ALS. This innovative brain implant enables him to communicate expressively and even sing by translating his neural activity into words almost instantly. The brain-computer interface, or BC-WINE, utilizes artificial intelligence to decode electrical brain signals during speech attempts. This technology reproduces features such as tone, pitch, and emphasis, allowing for a more natural communication experience. A study published in Nature on June 11, 2025, revealed that the system could articulate words within just 10 milliseconds of detecting neural signals, a significant improvement over previous systems that had delays of up to 3 seconds. Christian Herf, a computational neuroscientist, referred to this advancement as the Holy Grail in speech BCIs, enabling real, spontaneous, and continuous speech. To personalize the synthetic voice, researchers used voice cloning technology, training AI algorithms with recordings of the participant's voice prior to his illness. This approach ensures that the synthetic voice closely resembles his own. The research team implanted 256 electrodes in brain regions that control facial muscles, training the AI with thousands of sentences to accurately capture the desired pitch and intonation. The electrodes read the man's neural activity and generate speech sounds within 25 milliseconds, enhancing the potential for natural conversation. This system allows him to engage in real-time conversations and even sing simple melodies, with the AI adjusting pitches in real time. While Maitreyi Wairokar from UC Davis notes that the technology still requires refinement for improved clarity, the participant has expressed satisfaction with the system, feeling it reflects his authentic voice. David Brandman, a team member, highlighted the man's remarkable journey from paralysis and muteness to maintaining a full-time job and engaging in meaningful conversations. This ability to produce spontaneous speech marks a significant advancement in communication technology for individuals with paralysis, showcasing the potential of AI in enhancing human connection. On June 11, 2025, a team of researchers from St. Jude Children's Research Hospital, in partnership with the National Center for Genomic Analysis and the University of Adelaide, introduced a revolutionary single-cell RNA analysis technique known as STAMP. This method marks a significant advancement in the field, particularly in its cost-effectiveness. slashing analysis expenses from $3.56 million to just $75,000 for profiling immune cells from 1,000 individuals. This makes STAMP 47 times cheaper and more scalable compared to traditional techniques. STAMP allows for the simultaneous analysis of up to 1 million cells, far exceeding the tens of thousands typically analyzed by existing methods. The technique involves fixing individual cells onto microscopy slides, preserving their shape and gene expression, and utilizing fluorescent molecules to identify specific RNA sequences. This innovative approach not only provides quantitative data, but also enables scientists to visually examine cells, enhancing their understanding of gene expression in various health and disease contexts. In practical applications, STAMP demonstrated remarkable sensitivity, successfully detecting 2 cancer cells within a sample of around 850,000 cells, showcasing its potential in cancer research. Unlike conventional single-cell RNA sequencing methods, which often introduce bias based on cell shape, STAMP conducts its analysis on slides, ensuring a more diverse representation of cell types. The accessibility of STAMP is noteworthy, as most research institutions are equipped with basic microscopy capabilities, aiming to democratize single-cell RNA analysis for researchers without extensive funding or specialized equipment. The study detailing STAMP was published in the journal Cell and reflects a collaborative effort supported by various grants from the European Union and national research organizations. Key contributors to this research include co-first authors Emmanuel Pitino, Ana Pascual Reguan, and Felipe Sagado Dezem, highlighting the collaborative nature of this significant advancement in biomedical research. This has been your daily brief in science. To read more about these stories, follow the links in the episode bio. You can also subscribe to these updates via email at www.brief.news. For more daily podcasts about the topics you love, visit brief.news/podcasts. Tune in tomorrow. We'll be back with everything you need to know.